Can you guys hear me all right? Yeah, it's recording right now. Whenever I made the meeting, I set it up to do a automatic cloud recording. So I think it should be good. So the first step here is we want to go and download KiCad or KiCad. So you'll want to open Google, talk about, you'll want to open Google and just search for KiCad. So let me know whenever you guys get here. You're good? Okay. So just click the first link and then go to download and then click whichever operating system you have, probably Windows. And then you'll want to click GitHub, and then it should automatically start your download up here. So we'll give that a second. And then whenever this finishes, you can just double click. Did you guys all have a good spring break? Yeah. Okay. My download just finished. I'm gonna go ahead and double click that. That's almost done. Okay. Okay. Let me know when your download's finished. I don't want to go ahead without y'all. And you two in chat, you can let me know in chat if you want. Okay, nice. So once the downloads are done in here, we'll go ahead and go to the next step. Feel free to drop a message in here too if you have any questions or I'm going too fast or anything like that. Yeah, I know the internet in here can be pretty slow, so does it tell you how much longer it has? Oh, yours is done. Really? No worries. But let me know when that's done for you and then we'll move on. Yeah. Are you having issues to Dr. Parker? Dr. Parker. Just have like 2 minutes on the download and then we'll move on. Actually, Dr. Fauci, I'm gonna go ahead and move on because you're on a Mac, so your install will be a little bit different. You'll just have to drag it over. You'll double click and then drag it into the applications folder. So once you're here, you'll click next. I'll usually just install it for me. You'll hit next, but it doesn't really matter if you only have one profile on your computer. Keep all of this checked. These things are giving you the default schematic symbol libraries and footprints for your design so that you can design a little bit easier. You'll go next and then just click install. So we'll give this a second and then it'll install for us. Also, if anyone's on Mac, KiCad actually looks the same inside of the software, so there shouldn't really be any issues for you. Okay. Then once it finishes, you can just click finish and then it'll launch KiCad for you. And here you want to click start with default settings. Here, it's just asking if they can collect your data and basically send it back to themselves for bug fixes, basically. I usually click no here, but it's not really going to change anything if you do. And then here, this is your project window. You'll see all of your KiCad files here once you actually create some. It'll be like a folder, and then you'll have a schematic file, a PCB editor file, maybe your export files, different things like that. Library files if you import any libraries. Dr. Fathi, is your download good? No. Let's see. Okay, guys, we're gonna go ahead and get started with the project file. So to make a new project, you want to click the notebook right here with the yellow asterisk. It'll say new project. Click here, it'll let you name it. I'll name it ASTEP for today, or actually I'll name it ASTEP. And then you can save this really wherever you want to. And then here it's gonna ask if you want to automatically check for updates. I usually hit yes. Okay. So we'll click OK here. And then now you have your project file. So you want to double click your schematic here. It should ask you something about using the default libraries once my pop-up loads. Okay, so here it's going to ask if you want to copy the defaults, leave it as it is, and click OK. And then now you're here, you're in your schematic viewer. So is everyone here? Okay. So the first thing we want to do, we want to add in our components. We're going to be designing an inverter today. So you want to click Symbol Library Browser up here. It'll load your symbols and things. So it popped up behind. I usually won't use this in full screen mode, but it's not really, it doesn't really matter if you do or not. So you'll want to type in transistor on the left here. If you type tran, that should be enough. On the left side, by the way. You'll want to go to transistor FET, FET. And then on the next column, to the right of that, you'll want to click the 2N7000. And then if you double click that, it'll bring it up in your schematic window for you to place. Say that one more time. Oh yeah, I'll get her back through. What's going on? 2N7000. And this here, this is your N channel. Or actually, Jody, let me get you caught up real fast. Let me know whenever you're ready. Put down the component. You double click on it. Yeah. Okay. Yeah, like you see how I place it up there. Yeah. In the thing? No worries. So in the chat, if you're having any issues putting down your component, just close out of KiCad and then reopen it, and it should let you put them down. If you're going into your pick a component, your component libraries, and when you double click here, if you're not getting a symbol over here, just restart KiCad and that should fix your issue. Okay. So our next step, we want to come back here and stay in our FET transistors. That stands for field effect transistor, by the way. And then you'll want to search over here. You want to type in BS250. So that'll bring you to your P-type transistor. And you'll double click this here. And then this will give you another symbol to put down. And remember that your P-type transistors go on top and your N-type transistors go on the bottom. So now we have our transistors here. This is pretty important. You'll want to double click on the transistor, the one on the bottom, and we want to add in a simulation model for these transistors, or else we won't be able to simulate and make sure our circuit works. So when you double click, you'll click simulation model down here at the bottom, and then you'll want to use a built-in SPICE model. So click the little box down here. Then there will be a drop down where you can choose your type of device. So this here is our NMOS. So we'll want to choose in-channel MOSFET. Make sure you click MOSFET, not MESFET. So that should give you a window that looks like this. And then right below where you just clicked, you'll want to change your device type from VDMOS to classic quadratic. And then hit OK and OK again. And then now we'll want to do the same thing for our other transistor. So you'll double click that, go to simulation model, go to built-in SPICE model, change your device. Instead of in-channel MOSFET, you'll want to click P-channel MOSFET and be sure not to click MESFET. And then here again, you'll want to change device type to classic quadratic. And OK and OK. Jody, is your download done? Okay. Dr. Fatih, is your download good? Okay. Are you two caught up? Okay, okay. So the next thing you'll want to do, you want to go to the right and draw a wire. So click this little line here, or you can press a W on your keyboard. this will put you in wire mode. So remember, for an inverter, you want to tie your drains together. And then you'll also want to tie your inputs together. So you'll draw a wire from 3 to 3 on both of these transistors. And then you'll come off the inputs here on the left with your gates. You'll click so that if you don't click, you won't have like an anchor here. So it'll start going down like that. But it's not really an issue. It's just kind of me thing. So you go down and then you want to click on both of the dots of your transistors, and that'll tie them together. And then I also like to draw little wires off the input and the output. So if you don't actually end on a wire, you'll have this thing where it keeps trying to make you draw a wire. So you'll want to hit escape. You'll want to double click actually. You want to come here and double click, and then that'll finish your wire. So you want to go to the other side, grab your output, and double click again. And then this will give you 2 little probes. We'll add some jumpers here later. So next, let's add our supplies. You'll want to click the top dot on your transistor here. Bring it up a bit to give yourself some room. Draw over. You want to click here up in the top corner. Then you want to come down. Also, if you right click, you can move around your schematic like this. If you hold down right click, you'll click here to draw this part of the box, click here again, and then complete this by clicking on the circle right there. So right now you should have 2 transistors with these 2 drains tied together, the 2 3 terminals. And then you can draw this out if you like. And then you want to tie your gates together. And then you also want to draw a big loop here that connects the other 2 dots of your transistors. So to power this, you'll want to, instead of clicking up here on your symbol library browser, you'll want to go to the right and click here to go and place a symbol. So same thing here, just because this is a different library, it'll ask if you want to use your own or if you want to use the default library. You'll click here at the recommended one, just leave it as it's selected and hit OK. So this will load all of your spice things. Here we want to type VDC. Actually, I think I typed it. No, we're good. So you'll want to type VDC and then go to the folder that says simulation_spice and double click this voltage source, the one that looks like this. There's also a couple others that look like this. Don't click these. We want this one where it has 2 terminals. It's a 2-terminal device that we can change. So you'll double click this and then it'll give you a new symbol that you can put in your schematic. You want to place this here in the big loop. And then you'll want to double click this value, the little 1 right here. And we're going to change this to 5 because we're going to be operating at 5 volts. So change that to 5 and click OK. And then one other thing you want to click on your voltage device. And then this will bring up the properties over in your properties panel on the left-hand side here. So you'll want to scroll down to the bottom of this and exclude this from your board because this is just a simulation component. It doesn't have a footprint and it doesn't have a place in your board design. This is something you'd use maybe like a source meter, or in the past we've used the battery and connected that to a breadboard, and then that made current flow through our resistors. So it's a similar idea to that. So next, we'll want to add in our jumper cables. So to do that, we'll come back here to our component library or our symbol library. And then go to the far left side and type in connector. And then over here, you'll see a few folders for connectors. You want to click connector generic, and then grab con one by one. You'll want to put one of these at your output node. This is why I drew off to the side just a tad bit. Do that again. And then you'll want to come up here again. It should still be selected, but we'll need actually 4 of these. So double click here again. And then you'll notice this one's facing the wrong way, so we need to rotate it. To rotate, you press R on your keyboard. And then you can place it like that. So the one that says one by one. So when you go up here, you'll go to connector, make sure you click the connector generic library, then go over to the right side, and then it'll be the first one. It'll be the one at the top. It'll say connector one by one. And all this really means is saying this one here, you'll have two pins sticking up instead. So that's why it's 1 by 2, 1 by 3, 1 by 4, and so on. And they also have row connectors where you can get like a 2 by 2 connector or something like that, 2 by 4. I think you can actually go higher than this. No, maybe not in here, but I'm sure there's some connectors that are maybe like 3 by 4. So once you're here, you want to put these at your input and your output. And then you want to select this and get to the property similar to how we just did for the voltage source. But instead, when you scroll down in properties here, instead of excluding it from your board, you want to exclude this from your simulation. And then you'll want to come over here to the other connector and exclude this from your simulation as well. So now I'm going to teach you guys how to copy and paste. I'm sure you guys know how to do that. It's the same as if you were doing it in Word. You'll want to click this component here. And just to tell you the reason why we're copying and pasting, it's so that you don't have to keep scrolling down here and exclude something from simulation. When you're really designing a board or something like that, you want to be efficient. You don't want to have to keep going and redoing the same action. So if you can find a way to streamline that, you should. So you'll click here. You can right click and hit copy or press Control C on your keyboard. And then you can right click and click paste or press Control V on your keyboard. Then this will give you another header. You want to place this up here at the top, your top node, because this is where you're going to input your power at. This is where you're going to put your power. So then you'll want to come down here and do it again for your bottom node here. And this will be your ground input pin. So next, let's add some net labels to keep ourselves organized. On the right side, a net label basically names the node. So by default, it's going to name your nodes with like numbers, maybe like N001, N002, N003. But that's not really readable to us as humans. So we like to give it net labels. If you go to the right side, there's a little A with a line under it, and that's how you can place a net label. So you'll click this, it'll open up label properties. And then let's start with our input voltage, the voltage that we're putting at the input, which is our gate of our transistors. You'll want to type V in. It's standard to use the capital V and then lowercase n. IN, by the way. So you do that, and then it'll give you a little net label that you can drag in place. Put this on this input node, and then just click. And then now this net is labeled. So you'll want to come and do it again. But this time, instead of VIN, you'll do capital V, lowercase OUT for your output voltage. And then you can just put this here on your output node as well. And then you'll notice you don't actually have to keep coming over here to open the window. You can actually just click on a node here. It'll open the window up again. And then this is our V plus, this is our DC voltage. So we'll name that V with the plus symbol. you'll press enter, and then you'll have a label here. You'll click it down on this node. And then our last net that we want to name is our ground node. Oh, question. Yeah, the J pieces, you'll want to click there, scroll down, and exclude these from your simulation, but not from your board. And then to review this voltage source over here on the right, you'll want to click this one and scroll down, and you don't want to exclude it from your simulation, but you do want to exclude it from your board. Yeah. Voltage you want in simulation, but not in board. Connectors you don't want in simulation, but you want in board. Oh, oh, brother. Sorry, I missed that for a while. Zainab, did restarting the KiCad help you, or did you try to restart KiCad? Whenever you first opened these, we were getting an error where when you double clicked it, you couldn't actually put down your transistor. But restarting KiCad fixed that for everyone here at least. We'll walk back through some of these. Oh, okay. Are you caught up with us, or is there anything that you weren't able to catch? Okay, that's good. I just wanted to make sure we didn't leave you behind because I missed that for a while. I'll try to do a little bit better now. So, okay, next we'll need to put in our input signal. So you can drag components if you just select them the same way we did when we were going in properties. Click and drag your input over. You want to give yourself some room to put in your our input signal source, a V pulse. Because it's gonna have a really long spice parameter line that's gonna look a little bit messy if you don't give yourself some room. So this is gonna be a source similar to this over here. So rather than going into our library up here for components, we'll want to go back over here on the right side to place a symbol. So this will open up a similar looking window, but different libraries. And instead of typing VDC here, you want to type in V pulse. So you'll have this V pulse signal here. You'll double click it and place it down here. And then you'll want to go over back to your wire. Click the wire here. And then connect this over to your ground. Or actually, well, it doesn't matter. You can connect it down to your ground, or you can give it its own ground flag. But speaking of ground flag, let's go ahead and give our circuit a ground. So in order to give your circuit a ground, you'll want to go back to the same window. You'll go to place symbols, and then you'll type GND. That's the abbreviation for ground. So you type GND, double click here, and then you'll want to place it on this bottom node here. And then if I didn't connect this, I could go back over here, grab another ground, and then just place it down here in case you don't like this long wire right here. Also, to get out of any tool, you'll notice like once we put something down, it'll keep us in that same tool like this right here. You'll see that little op amp symbol right there to tell you that if you click, it'll just open up that window. But if you don't want to be here anymore, you'll hit escape on your keyboard, and then you can go back to select things again. And say you could select this wire, press delete on your keyboard and delete it if you wanted your schematic to look a little bit cleaner. But because these are both flagged with ground, it knows that they're at a common voltage. Okay. And just like our other source over here, we'll want to exclude this source from our board. So you'll want to select this source, scroll down in your properties, and then exclude this from board. Check exclude from board and make sure not to click exclude from simulation. Okay. So next, this is about it for our schematic. Well, we want to simulate this and make sure that it works. Well, actually, one more thing. We need to edit our spice parameters for our V pulse because right now TW stands for your pulse width, how long your signal is on, and then your period stands for your full wavelength, how long it takes for your signal to repeat. So if you double click here, it'll open up this window here. It'll give you symbol properties. And if you scroll all the way down to the bottom, you'll see a field called sim params. That stands for simulation parameters. And then here is a netlist line. So for us, we're going to change TW, our pulse width, to 1M, which is 1 millisecond. And then we'll change our period to 2M, which is 2 milliseconds. And I'll give you guys a good visualization so that you can understand really what a pulse width and what a period is once we make it to simulations. But you'll hit OK here. And then now we should really be done with our simulate or our schematic. So up in the top right, you'll see an icon that has a waveform on it. This is how you open up your simulator window. So you can click here, open up your simulator. And then if you click the play, it won't actually do anything because we don't have any spice. We don't have a spice directive here yet, but it will give you a little window to help you edit. And for us, we'll want to run a transient analysis. So tran is here. For our time step, we'll type in 1U, which stands, it's really 1 micrometer or 1 microsecond. So that's I'm gonna show you guys this really fast. So basically you see here, this M here is milli, and then this U here is really micro. So 1,000 microseconds would be 1 millisecond. So that really means we're taking like 1,000 samples per second per pulse width. So here you want to set your final time to 10 milli. That'll give us about five cycles to look at. And our initial time will be 0. And then once you do that, you can click OK. And then that should run our simulation. But you'll notice there's not actually anything plotted here. You'll have to click the plot button over here to make it plot. You'll want to plot your V in, and your V out. Oh, okay. So you'll see here, our simulation doesn't actually look exactly right. That's because over here, we didn't change the second unit on our V pulse. If you notice here, we used 5 volts as our power, but our input signal is going from Y1, our first value is 0, to Y2 equals 1. So our second value is 1. So it's not actually giving us enough to turn our devices entirely on. So to fix this, you'll want to double click on your V pulse source one more time, then go back to your sim params, and then change this Y2 to 5. And then press OK. And then if you click here again, it'll open your analysis window. And if you hit play, it'll update your simulation. And here you can see now our inverter is working well. So now you guys don't have to follow along for this part, but I want to show you guys a little visualization of what really is pulse width and what really is period. Oh. So it'd be best for you guys just to watch this for a second. So let's come back over here to our simulation parameters, and then I'm gonna play with the TW, which stands for our pulse width. We're gonna set this to 0.5 mil, so half a millisecond, while leaving our period at 2 milliseconds. So our pulse width is really a fourth of our period. So when we come back over to our simulator window, if we run, Awkward. Oh, okay, hold up. My bad. I didn't hit OK, so it didn't actually update the parameter. So we come here, click play. You see this line over here shifted. That's because if you look at our input voltage, it's only going high for half of a millisecond. It's going high for a fourth of the period, even though our period is still at 2 milliseconds. So that means it's high for half a millisecond and low for 1.5. And then if you go look at your output, you'll see this reflected. You'll have it low for that same period of time and then high for that same period of time, even though our period is the same. So let's go back over here and then change this to 1.5 pulse width. 1.5. Okay. And then if we run our simulation again, you'll notice this line, instead of being here, it's going to move over to like right here. And then you can see that means that our Vn is going high for that 1.5 milliseconds, even though our period is 2. So it's going to be low for the rest of that period. And then one more thing to show you guys real fast is, let's say we set our pulse width longer than our period. What do you guys think would happen? Any ideas? So let's see. So let's set our pulse width to 5 mil, click OK, and then run our simulation. So you see, it's just a flat line. And that's because your pulse is high longer than your period. So your pulse is trying to stay on for 5 milliseconds, even though it's getting cut off at 2 milliseconds and then repeating again. So you're not actually seeing any changes if you do that. So you want to make sure to keep your pulse width lower than your period. Generally, you'll want this to be half of your period, which is why we're using one for our pulse width and then 2 for our period. Okay. So hopefully that helps you guys understand really what a pulse width and what a period is. We'll go back here just to make sure things are still working well. Okay. So now that we have our simulation working, we'll want to start working on our layout. Well, I'm going to move this out the way a bit. Down here, this is where you can put like your name, the title of your circuit. We'll skip that for now just to save on time. But if you did want to do that, you can add text. Down here on the bottom, there's a text box. You could say, just draw your name. My name is Nolan. You could say Nolan, whatever your name is. You could put it down here. And then if you want to change the size, you could click here. There's a text size box. You could say, put that to 200, bigger so that you can read it. We won't go into that too much here though. So before we start our layout, we'll need to get footprints for these headers that we added. So to add a footprint to our header, you'll want to select it and actually double click it. So when you're in this menu, you want to find the field that says footprint here and then click on it. It'll bring up a little typer thing, but what you want to hit is these 3 books right here so that we can browse. So now up here, you want to search and type in connector. So here you want to actually type in the full word connector underscore pin. So let me know when you guys get there, because I don't want to leave you here, because this window can be a little bit confusing.
I've been taking notes, but I'm still, but it's like loaded, and I don't know if this is what.
Oh, okay. Well, give us 1 second. We're catching up a student who was having issues downloading. So once we get them caught up, we'll come back here, get our footprint set up, and then we'll be ready to go into the board layout. So just take a quick break for 1 second if you're caught up. So when you go to you want to double click on your header, double click here. And then similar to how we went to the SPICE parameters, there's fields down here. You have a footprint field. You'll want to click on the value. And when you click here, you'll have 3 books right here. And if you click these 3 books, it'll bring up this menu where you can search for footprints. And then what you'll actually want to type here, you want to type connector underscore pin. And then we'll be using the connector pins from the 2.54 millimeter. That's the generic. And if anyone wants to like move ahead, we'll actually be using this first pin header here, the vertical one though. If you notice, there's different horizontal ones, but that's not what we want. We'll use the vertical, and then you can see here, there's like the things where we saw it was like, you could have a 1x2, 1x3, 1x4, 1x5 sort of thing. If you click through these, you'll notice that there's all different sorts. And if you scroll down, there's all kinds of different sort of connectors that you can have.
What is that first
It's actually the second one. Yeah, you want the vertical one, but it's still one of the first two. The first one's just a horizontal pin. That'd be like something if you had it going off the edge of your board, but that's not what we're gonna have for today. So 1 second and then we'll get moved on.
It can be less.
One second, I'm gonna pause the recording until we come back. Okay, guys, we're all cut up now and we're ready to move on. So to review, let's go back and start from scratch on how we can add these footprints. We'll have to do this to all four jumpers, by the way. I probably should have done this before we copied them. So in the future, if you are working on a board, that would be a good thing to do. But it won't be a huge problem here since we don't have a huge number of jumper headers. So you'll want to double click here. You'll want to scroll, you want to find footprint, click here, and then click the 3 books here. Once you have the 3 books here, you want to type in connector _ pin. And I'd recommend pressing Control A and then Control C to copy this so that you don't have to type it out 4 times. Or you can just click drag, right click, copy, anything, whatever's comfortable for you or you know how to do. So the next step here, you want to go down to connector 2.54 millimeter. And then you don't want to click the horizontal one. You want to click vertical because we want our pin headers to go straight up instead of going out over the edge of the board. So you'll click that and then you hit OK. And then hit OK again. So now you have a footprint assigned to this bottom jumper, but we'll need footprints for the rest of our jumpers too, or else we'll run into some errors in our layout. So double click this jumper, go back to footprint, hit your 3 books again. Oh, it actually saves this, so you don't really need to copy it, but keep the same footprint here, press OK. You can check to make sure it worked because this field will change. Hit OK again. Say it again. Did you click on the value field? So when you double click on here, you want to click value right here. You should have like kind of an editor there. And then on the right side, it should pop up.
Yeah. Sorry.
No worries. It can be a bit confusing when you're first learning. So you hit the 3 books on the right side, and then you'll want to type in connector _ pin. And then it should look like this whenever you type in connector _ pin. You'll go to the 2.54 millimeter and then select a vertical header. Then once you have that selected, it'll turn blue. You can press OK. You can look here to verify that it's there and then hit OK again. So now We'll add it to this last one here. Oop, good check. And Zainab, are you still good? You're still with us? Just give me a quick message if you need any help or anything's not working for you. So here's our last vertical. And then now we have all our footprints set. So let me know when you guys are all done with it and have all of your 4 footprints set. You all good? You all good back there too? You all good with your footprints? Jody, are you all good with your footprints? Okay. So the next step, after you have your schematic set up, you'll want to update your PCB document from your schematic. So to do that, you'll press tools up in the top, in the head bar up here. And then you want to update PCB from schematic. So give it a second to do this. And then you'll want to hit update PCB. And then hit the close, or it should close on its own. But if it doesn't, you can hit the close button. And
No, so I'm getting the update PCB from schematic, just hit update PCB. Correct?
yeah, yeah. And then you should see something like this. If you scroll in, you can zoom in and out. Scroll on your trackpad or mouse, whatever you're working with. You can zoom in and out on your components. But initially, it'll move them all together. And then you can just place them down by left clicking. Say that again. Give it a second. Wait for your mouse and move your mouse around.
Yeah, that's all I'm doing.
Yeah.
But there weren't, errors.
Okay, guys. So if you look here and then you zoom in, you'll be able to see these little blue lines. They're kind of skinny and maybe hard to see, but these are like your net strings. These show you what connections need to be made where. So if you look here on our transistors, you can see it tells us which pins need to be connected together. Our V out node tells you these V in nodes need to be connected together. and then it tells you which one is V plus and which one uses ground. So using that information, we can tell that this is our PMOS on the bottom and this is our NMOS on the top. So let's start moving our components around. To move around your layout window, you'll want to right click the mouse and then you can move around, zoom in and out with the scroll wheel. If you click something, you'll select it. And then if you click and drag after that, you'll move it like this. If you want to move multiple things at once, per se, you can click and drag with the left hand, with the left mouse button. You'll select multiple things, and then if you click and drag, you'll move multiple. But you can see sometimes you can accidentally select too much. You see, I got the header labels there. So what we'll do, we'll grab our two transistors and put our 2N7000 on the bottom. And then let's put our Q2, our BS250 on the top. And we're just gonna do this because it'll match our schematic. Because our B, if you look at the schematic, our B250 is our PMOS up here. And then our 2N7000 is our NMOS down here. And by the way, Q is kind of the notion for a transistor. And that's why it's called Q1 and Q2. Except usually, sometimes you'll see like MOS1, MOS2, something like that. Q is generally used for BJT style transistors. So now that we have these over here, let's start drawing some traces. So to connect these and get rid of these blue lines, you'll want to come over to the right side and then click this little button here, which says Route Single Track. The shortcut for this is X. But we'll click this button here. And then we'll come here. It'll kind of snap here for you. Let's first write our V out. So we'll drag this, click this, and then we'll drag it up. That kind of bothers me a little. If you hold shift and move this like kind of above it, hold shift on your keyboard while moving it, it'll get you like perfectly above so that you don't have any traces that kind of curve. But it doesn't really matter. It really doesn't matter that much, especially for something like this. So once you have your trace thing clicked from here, or if you press X, it'll kind of start drawing a trace wherever you are. So if you use the shortcut, you want to already have your mouse like there, wherever you want to start your trace when you press it. But if you end up in this situation, you can just press escape and then you'll still have your trace tool selected. So come here, click V out. It'll highlight anything that you can actually connect this to. But we're going to be connecting these here and then moving our jumpers in better locations afterwards. Whenever you're laying out a PCB, you definitely want to do it in pieces. Because if you do too much at once, it'll get way too confusing, especially once you get to like more complex PCBs. I'll show you guys some of those towards the end of class once we finish our layout. So you just drag this up here, click. You can come back here again, click, drag this up here, click, and then now your transistors are tied together. So these two connections we just made here, if we relate these to our schematic, it's these two connections here. We've tied our gates together and we've tied our drains together. So next, we'll go ahead and add in these connectors that we excluded from our simulation so that we can actually put a signal in and take a signal out with the jumper cables, or you could use alligator clips, any kind of electrical conductor or any kind of connector. So if you zoom in, it'll actually tell you which net goes with what. So we want to grab this J2, the one that says VN, whatever. It may not be J2 for you if you put them down in a different order than I did, but click whichever one says VN as its net here. And you'll want to put this over to the left of your transistor. Or say if you put your transistors down the other way, the opposite way than I did, if your transistors look something like this, your VN would actually go on the other side. The main idea with these blue little net strings, I kind of think of them like spider webs. You don't want them to cross, because whenever you cross, when you have crossing nets, you'll need something called a via to finish that route, because you can't, each of these are copper traces that are on one layer of your board. So you couldn't, if you had your VN on the other side, you couldn't just run your trace straight through here. It'll be blocked. It'll cause a problem. It'll cause that trace to, you'd have to like route your VN trace. You'd have to go basically all the way around with this and then go all the way. You have to go like this or something, which isn't super ideal because you're adding a lot of parasitics, but that's not really important for you guys today. Today, you'll put this on the same side, whichever one's closer. We know this VN is closer right here. We'll come back to our trace tool, click on VN, click here. And then now you have that connected. And you can see as we connect these, you'll notice these blue lines start to go away. The blue line is really just showing you the shortest path to whatever node you want to get this to. So next we'll add in our V out pin. We'll drag this over. And then you'll want to press X or grab your tool from the side again. Remember, if you press X, you want to put your cursor over this to start because it'll start you off wherever you press X. But you can press escape if you end up there. So connect this over here. And then now, to relate this to our schematic, we basically have our inverter finished. Our inverter is done. But we always need to give our circuits power. So to give our circuit power, we're gonna grab these other two pins here, our V plus pin and our ground pin. And let's put this up towards the top for VDD or for our V plus. Also, to move multiple things at once, you can click with left click, drag, and just move it if you want some more space so that we don't go over the edge. And then for our ground connector, we're gonna put this at the bottom. We're gonna put this at the bottom and top because generally when you think about a circuit, you think of your ground as being at the bottom and you think of your positive voltage as being at the top. So next, you'll grab your routing tool and press X or grab it from the side, and then you'll route these up to where it highlights. You'll route these to the pins of your transistors that get highlighted. And it actually won't let you route to the wrong pin, which is a nice little training wheel feature that most PCB softwares will offer for you. So now we wanna add an edge to our board. So if you look on the right side of your window, you'll see all the different layers that you have. You'll have a front copper layer, a back copper layer, solder paste, different things like that. But what we're interested in is this edge cut layer. There's a layer called edge cuts down here it's kind of towards the middle, but towards the bottom if you're not scrolled at all. So you'll want to select edge cuts, then you'll want to go down here to this tool button and draw a rectangle. Click the rectangle. You want to come down here to like the bottom left of your board, kind of eyeball this a bit. If you do mess it up, you can just press Control Z to undo and then redraw the rectangle. So like say for example, I do my rectangle wrong. It's like, oh man, what do I do now? You could come over here and stretch it out like this. You can always stretch your corners, or you can just press escape and you can Control Z it and just redraw it, whichever one's easier for you. But if you want to edit a board, like say you already have things put down, but you have to move something. Maybe this pin is a little too close or something, and you want to move this higher up. You can just click and drag this up, but we're not going to do that. So once you have your edge cuts, you can actually do a cool thing and look at your board in 3D, kind of look at a preview of what your board would look like. You can go to view here, go to 3D viewer. And then here you kind of see, you can get a little preview of what your board looks like. If you left click, you can move around, move the angle, and see your board, which is pretty cool. Yeah, there should it's you see this little 3D preview, the one up on yeah, EdgeCut tells the simulator or the layout software where you want these edges on the board. Is that what you're asking? Let me see. Oh, okay. So guys, we're just about done now, actually. We're gonna do a couple little things that are kind of more for aesthetic and readability of your board. Because like you were saying, generally when you design a board, the person using it isn't always gonna be the person who designed it, right? So sometimes it's kind of like matching words to a song that you've never actually heard before, right? It's your cadence will be off, you won't know the tempo or anything like that. So over here, you'll notice these yellow kind of letters here. This is your silk screen. So a lot of times what I'll do, say this is the VN pin. I'll double click here and change this reference from J2. If you double click on it, you can change the reference, which is kind of like the comment. And then we'll just name it VIN. So that'll make this VN. So if you go back over to your 3D viewer, it'll actually update automatically. And you'll see this VN right here by this pen. And I'll usually like put this towards the edge. You can click this and then move it just like it's a component. I'll usually move this out to the edge, or you'll get a better, it's kind of like an intuition you build. Where's the best place to put your comment? And the best way to start learning that is just look at your board in the 3D viewer and think about if you would see it. If imagine if you had this board in front of you, would you see this? Is it too small? Is it too big? Are the letters too thick to the point where you can't read it? It's kind of like it's really PCB design is really a lot like art. So next we'll come over here to our V out. Let's double click the designator right here and change this to V out. And then let's move this over to the right side. Then last, or we'll have our two other connectors here. We can name this one G and D. And then J3, we'll name this V plus. Then I'm gonna move my board edge up a little bit just because I'm kind of running into it with my silk screen. Okay. And then also for your transistors, they're called Q1 and Q2. If you look here, this could be a little bit hard to see. Usually I'll try and keep my designators in the bottom left-hand corner for components. So I would just drag this down here, something like that. Drag this down here, something like that. Then when you come back and look at your 3D viewer, you'll see that I would probably move the Q2 over a little bit more, just like to the left a tad. And then, so your board is mostly done. One kind of pretty thing to do to make your board a little bit prettier that we'll usually, or I'll usually do at least, is I'll come over here. You'll go to f.silkscreen, which means your front silkscreen layer. And your silkscreen is kind of like a print layer on top of your solder mask. The solder mask is the green part of the board. It's what makes your board green. And then below that, you have copper, FR4 layers, prepreg, whatever dielectrics that you choose. We'll talk about layer stack ups once I show you my boards at the end. I didn't really want to go over that in the beginning because I thought it might be a little bit too overwhelming. And we weren't going to change the layer stack up for this board anyway, so it wasn't really relevant. So you'll go to your front silkscreen layer, grab a rectangle, and you can draw this actually around your edge cut. I'll generally keep this at the same as the edge cut. You'll click, press escape to get out of that tool, and then double click on the line. Once you have that made, you'll double click on the line. And then here in this window, you'll see something that says line width. We'll want to change that to like maybe, let's do like 0.5 millimeter. You can see the units are set for us here in millimeters, but let's just type in 0.5 and then that'll make it a tad bit thicker. So if you go back over to your board, you'll see now we have a little white line around the outside. And then we could even make this like one millimeter. You can double click on the line again. But line width, it's really up to you. It's really personal preference. As long as you're not, say, imagine I made this like 10 millimeters. We're running into our silk screen. Now you're losing information in your board. So double click that. We'll just make it 1 millimeter. And when you look here, you have a nice little border around your board. Just makes it look a little bit, oh, sorry. Yeah, it just kind of makes it look a little bit more like maybe professional, just better, fun, more fun to look at. I just like to do it. One of my TAs named Abdel showed us how to do that for our microwave circuits, and I've just kind of adapted it since that point. So you'll want to double click on the line here that you drew. Did you already get your silkscreen line down with the rectangle? No worries. And then lastly, say a lot of times I'll like tag a board or something like that. Let's just use the iCastle PNG for the time being. Actually, I want to use the picture, but if you come down here, you can go to text file. You can go down to text file, type in text. I'll put in my name, LNR. You could put in whatever your name is. And then make sure down here on the layer, you're not on any other layer. You want to put it on the front silk screen. And then you could also change the width if you want, or the size of your name. You can just come down here, place it somewhere convenient. And then if you want to change, if you want to change anything about it, you'll come here, double click your name. You see you can change the width, which is your width is going to be like, oh, let's check this. Yeah, your width is going to be how stretched out your name is. So we'll keep this at 1 for the time being, and then height, you can change how tall your name is. You'll probably, yeah, the front silkscreen layer. But I'll just keep this at 1 and 1. Thickness, change how thick the font is. And yeah. So if you go back and look at your board, you'll see you'll have your name right here. And then you could even name the board if you wanted to, so that in the future, say, if you're making a lot of boards, you might not actually remember each individual board just by looking at it. So we can name this inverter. So that anytime you come back around, you know that this is your inverter circuit. So nice. And with that, we're just about done with the tutorial. So this is how you would make a basic board inside of KiCad, FreeCAD software. And lastly, I'll show you guys how you actually export your manufacturer files in case you actually want to get this board fabricated or something. So to do that, you'd come back to your PCB layout. You'd go to File. You go to File, Fabrication Outputs, and then you'd hit Gerber. You want to get your Gerber files, get Gerbers, and then you'll want to just hit Plot. I wouldn't really recommend changing any of this in the begin. Like as a beginner, it's going to select the ones that are probably the best for you. If you start clicking things, you might start losing stuff. Say if you accidentally click that, you'll lose all of the front silk screen that we just worked on. And when you upload the board, you'll be like, huh, why does my board look so plain and empty? So you'll hit plot here. Plot there, and it should output your files. Also, the default directory is wherever you make the file. But you can hit this folder right here to change that if you'd like. Say if you want to put it on your desktop or something, or maybe you have like another file somewhere for some reason. Yeah. So next, the other thing that a PCB manufacturer will need are drill files. And KiCad actually makes this pretty easy. In the bottom right-hand corner, you can click Generate your drill files. And then it'll open up your drill window. But we'll leave this as the same default folder. And then you'll hit Generate here. So that will give you all your drill files. And in the event that that wasn't there, drill output is also over here in fabrication output. So you could come here, get your drill file, and it's the same window. You can just generate like that as well. So over here, there's other fabrication outputs. And most of these are actually just like different file types. Think about how music can be like an MP3 file, it can be a WAV file. It's a different format of fabrication file that you can send to manufacturers. But the most popular are Gerber and drill files. And then you can also export a bill of materials. Say if you were designing a circuit for a company or something, they'll want a list that looks organized of what do we need to buy, what's the prices of these and things and so on like that. So your bill of materials will hold that information. You can export that easily out of your CAD software. Component placement, this is usually called a pick and place file. It's a big text document with numbers basically that your manufacturer can upload to their drill machine. And it'll tell the drill machine where it's, or actually no, this is for components. If you have, usually I'll assemble the board myself, like solder it and stuff like that. But if you're designing something on a mass scale, you can't, hand soldering each individual component isn't really feasible. So you can give them pick and place files for where to put the components so that they can do like wave flow soldering, different things like that. Footprints, yeah. And IPC it's a national standard. I can't remember exactly what it stands for, but I'm pretty sure it's like international something. We'll look at that real fast. Okay. Institute for Printed Circuits. So these people make most of the standards that we should follow, different guidelines and stuff like that to make sure we're designing circuits that are going to work and be reliable. So now that we have our files exported, we'll open up our file browser, our browser window, and you'll want to go to wherever your file is saved. By default, you'll go to Documents. These will save inside of Documents. And you'll go to whatever you named your file. I named mine ASTEP type. And inside of here, you can see these things here. These are your Gerber files, and your drill files are also in here. So what you'll want to do, you want to come out of this folder, you want to right click on it, and you'll want to compress it to a zip file. Or if you have 7-zip or something like that, you can add it to an archive, something like that. But the main idea is that you want to get a .zip file, because if you upload this to a manufacturer, they're going to want the zip file, or else they won't let you upload. So to show you guys just an example manufacturer, we often use JLC PCB just because it's so cheap. They make good boards for very cheap. The boards themselves are like $2 or something like that. So you'll go up here, you'll go to order now. It'll probably make you make an account. I actually have one. You'll go to add Gerber file, you'll upload, and notice right here it says they only accept zip or RAR files formats. So that's the whole reason that we zip those up. So you'll go to where your zip file is, you'll go here, click open, give it a second to load up your file, and then you'll get a preview of your board, actually. So here, now you can see this is the board that we just designed. It matches our little 3D preview here that we saw. So down here, it'll ask about the base material. It'll ask about how many layers of your board do you have. This one, we just have a top and a bottom layer. So it's just a 2-layer board. A really popular board is a 4-layer board. You can go up to 6, but boards, as you can see here, there's lots and lots of layers that boards can have. It can get really complex for, like, say things like commercial motherboards, graphics cards, stuff like that. The boards are going to be really complex. So here, the dimensions of your board, it'll have this information automatically from your Gerber file. Here you can select how many boards that you want. The lowest number you can select is 5. So whenever you're getting boards, you'll always kind of get them in packs of 5. Unless you're doing some sort of like industry thing, maybe you'll get 80,000 boards for how much money? For $4,000. But for us, we just need 5. We just want boards that we can play with. So once you're done with that, you'll select industrial consumer electronics. Here you'll just want a single PCB, the delivery format. Whenever they make PCBs, they'll have like a big substrate, and then maybe there will be like 5, 10, 20 boards on this one like panel. So if you're doing something for commercial things, they may have like a panel designer that they actually pay, or maybe you're the panel designer. Maybe part of your job is to actually make the panel for the board. Because if your board isn't if stacking the boards isn't the exact height or length of the panel, you will have some wasted panel, but you're more than likely paying for that one panel. And then you can get panels by JLC PCB, but the panels are more for if you're getting more than one circuit design. But here we just have one single one. They'll do all the panel stuff for us. Here you can change the PCB thickness, but this is generally set by your Gerber file. You can change your layer stack up. It should pick this automatically. Then here you can change the PCB color. And what this really means is you're changing the color of the silk screen. So remember we said there's going to be different layers. There's going to be like FR4 layer, which is just a dielectric. There will be a pre-peg layer. Then there will be your copper layers for your conductor. And then on top of all of that, they'll protect it with a silk screen layer, the green thing that you see from boards. But really, you can make it any color you want. You can have a purple board, you can get a red board. I like to do black boards. They look pretty cool. But yeah, if you select a white board, it'll switch the color of your silk screen to black. But most other boards, you'll just have a white silk screen over it. And this doesn't really change the price of anything, nicely enough. So let's just go with black for the time being. Surface finish, I'll usually leave this here. I won't, this one is made of like some sort of gold. It's this here versus this. If you hover over the question marks, it actually tells you about each of those. This one's more affordable, uses tin and lead. And then this one uses gold. It's a more popular industry standard because it's less loss, better. It's just overall better. Um, so yeah, I guess we should address the elephant in the room. Lead can be kind of bad for humans, for people, but it's not really going to be a problem for you because you're not actually manufacturing the board. The lead is going to be like in the material and not really leaving out into the air for you to breathe in. Usually in electronics, my friend Alex, he says usually the dangerous stuff is the good stuff. So you could always choose this, but it's going to be a little bit more expensive. And I mean, it's really not going to change anything in the grander scheme of things. I personally don't know the main differences between the two. I guess just that it doesn't have lead, and then they probably replace lead with some other material to replace its function. But I really don't know too much about that. So here, next you have your copper weight. Your copper weight actually ends up being like how thick or how wide your copper trace is. It's how much copper per millimeter, I believe, is actually being used on your board. So if you're carrying more current, which we're not, you might want to go to like a 2 ounce copper thickness or something like that. You'll pay a little bit more. As you can see, this that made things a lot more expensive. So sticking to 1 ounce is usually good just because it's very standard. So here you have your via covering. Basically what that is, here you can have tinted vias that kind of cover most of the copper. You can have untinted vias that just leave the copper exposed. You can have plugged vias, which place basically some dielectric with the silk screen over it so that it's non-conductive. And this is good for, say, here you see there's two SMD pads, which stand for surface mounted technology or surface mounted device, SMT, SMD. If you have these pads like this that are really close together, solder may try and wick from your pad to your via while you're soldering. If you're not super careful or just not super experienced at soldering, that can happen, and then you can cause a short circuit, which would be pretty bad for your board. You'd have to get some solder wick to get the solder off, or find some other method, or maybe move and use one of the other boards they sent you if the situation's really too bad. So next, this is just saying the minimum diameter, how precise you want your board to be. If you go up, usually you'll end up paying more for any kind of changes that you make. Confirm production file means once they're ready to put it into production, they'll ask for you to confirm to make sure everything is good. Usually I'll select no just because it'll get things rolling faster. But if it's like a really important thing, really expensive board, maybe sometimes it could be useful. Here, they'll actually print order numbers somewhere on the board. You can request them to remove the mark if you want to. Let me see. I don't know if that costs more. Yeah, it doesn't cost anymore, but I usually just leave it on. It doesn't really matter that much. So this you can't really change. This flying probe test is just to make sure that your board is actually electrically connected. It's like a continuity test, if you guys know what that is. So gold fingers, I actually don't know much about these, but kind of looks, if you guys know what GPUs look like, it kind of looks like a little thing that you slot into that. So I've never actually used that before because we haven't used any connectors like that in my lab, but I'm sure that's what that is. Castellated holes kind of has it's like little arc holes at the edge of your board. I'm not sure what these would be used for. And then edge plating just puts copper around the entire edge of your board. And you'd probably want to ground this. That'd probably be good for like electromagnetic shielding and things like that. Then down here, you have advanced options. 4-wire Kelvin test is just, it's kind of like a fine probe test, but a little bit more robust. Paper between PCBs, you wouldn't really ever do that. IPC again is the International Printing Institute for Printed Circuits. Here your silkscreen is just asking how you print that. Inkjet silkscreen printing is fine. And then the last one is the box. So I'll show you guys what a JLC PC box looks like. So you'll get like a blue box like this that has the JLC PCB logo on it. And selecting no logo, blank box will just, you'll get a blue box, probably. I've never actually ordered it without the logo, so I don't know if the box color changes. And then PCB remark, this is any comments, any special requests you may have. And then like we were talking about pick and place files a bit earlier, if you want your board to come assembled, maybe you're getting like 1,000 of these, you don't want to hand solder them by yourself. You can turn this on and they'll actually put your components on for you. But to do that, they'll need a bill of materials. So you'll have to export that BOM file that we were talking about earlier. And then you'll usually have to pay them, you'll have to pay the cost of the components and probably pay a little bit of labor. And then the last piece is a stencil. We actually just got one of these for our lab. This wouldn't really be super useful for your boards that you're designing now, but say you have, we talked about SMT or SMD components, which are surface mounted. Those ones can be pretty hard to solder. Let me find. What's the plug be? Okay, this. So here you see like these pads here, these can be pretty small and they can be hard to solder to. So if you have a lot of these very close together, a lot of times you'll get a stencil file or a stencil made, and then you can use solder paste and kind of scrape it over the stencil, and it'll leave solder paste over those pads. And then you can go through with your components, place your components on those pads, and then use something like a heat gun, put it in a solder oven if you have one available to you. And it'll make the soldering a lot easier and less tedious. So once you have this done, we'll get rid of the stencil. You could save this to your cart. A lot of time, I wonder, I really don't know if it's because I've ordered so many PCBs or just because this one's smaller. Usually the PCBs will come up to like $2. So you can save that to your cart, view carts, or like you can see this one. I went through it one more time last night to kind of remind myself. But once you're here, you'll select whichever board that you want to get made. And then this estimates your shipping. But there is one shipping option down here that's like $1.50. So if you really do want to get a board made, you could get one made for like $5. But keep in mind it's gonna take a while to get to you. So in situations where you like need the board quickly, where it's a time constraint for like maybe research or something like that, you'll usually want to pay this extra cost for your shipping. And once you get like bigger boards, if you have a pretty big board, the shipping price can go up from $17.50, but this is the base price. So you would go secure checkout, shipping address. I have a couple here. We'll just use this. And then you go to continue. DHL Express keeps the $17.50, but if you come down here to global standard line, you could be done. You could go continue, $5, pay directly, and then it'll take you to like PayPal, different stuff like that. You would go to submit order. And then you would just pay PayPal, credit card, different stuff like that. And then they'll often have these different coupons that you can use if you spend enough money. But yeah, let me go back here because I think that might have actually put that into production. I don't. I'll come here, hit cancel order. Okay, so yeah, we cancel that order. But if you did want to order PCB, that's how you do it. So that kind of concludes our tutorial on how to design PCBs. So now I'll show you guys some more complex PCBs. I probably couldn't make anything like this that you see on the loading screen, but it really does show you just like how far this can go. You know, all these PCBs are connected and talking to each other. And you can also have things, I'll show you that real fast as well. There's actually flex PCBs. You can have 1 to 4 layer PCBs, 6 to 32, have them assemble things, but there's also these flex PCBs, which is what you generally find inside of like a smartwatch or something like that. I've never designed one personally, but I think the design would be the same. It just kind of changes the substrate that you'd be on. You may have to change your layer stack up a bit to be a bit thinner. But yeah, I'm not sure like how many layers, how many different things they have for that. So this program, this is a paid software. This is like the industry standard for PCB design. It's called Altium, but KiCad really does compare very well to Altium, especially for being a free software. Mm, So I'll show you guys my senior design project board. So this is a little board that we made. What it does basically, we have a bottle dynamo hooked to a bicycle. And the bottle dynamo is a little dynamo where if you spin it, it'll put out an electrical signal. So putting it up against the bike wheel makes it turn with the bike wheel's friction. And as you pedal the bike, it's going to put out an AC signal into this N plus and this N minus that goes through this. These are 4 diodes in a configuration called a bridge rectifier, a full wave bridge rectifier. So that's going to turn this AC signal into a DC signal. So instead of having a little sine wave, it's going to go into a flat DC voltage. And then that's going to go over here to a third-party board that we're using called a Pololu board, where these pin headers are spaced the same. Let me put the Pololu real fast. Pololu. Voltage regulator. So this little board here, if you look here, there's these through hole component. There's these through holes on them. This one here particularly. There's these through holes here, and then this one here. So over here on this board, we'll put another pin header here, and then put a 5-pin header here, and you can just sit the other Pololu board on top of this, and then it'll work pretty well. In our first iteration, it worked. The board fit. So this one, we took out a few things from my first board. And then over here, you can just plug in any generic USB port. And then as you pedal the bike, it'll charge your phone and things like that or whatever. So that's our senior design project for the year. Then I'll show you guys two more boards and then that'll be about it for today. So this one is a timing board for timing measurements. And basically what that means is that you have your signals. So think about the whole signal that we were sending into our inverter. You send one that goes up and down and up and down and stuff like that. But it was happening only like every one millisecond or 2 milliseconds, right? So fast, that's not like how fast our general circuits are actually going to move. Your CPUs, even in your phone, you're going to be dealing with like 6 gigahertz, 8 gigahertz, just like really high signals that are going to be in like the nanosecond or about around the nanosecond range rather than the millisecond range. And just for scale, millisecond is to the like 10 to the -3, while the nanosecond is 10 to the -9. So it's a lot faster. You have 100,000 nanoseconds in a millisecond. So really general, like real electronics are moving 100,000 times faster than what we designed for. So here, you can see all these little squiggles in here. This is called link tuning. So the important thing about these digital signals is you need the signal that you put in at these SMAs right here. These, you can think of these almost as the headers, but it's a big boy header, a big strong header. So you put a signal in here and you want it to reach this thing called the DUT, the device under test. You want them all to reach the DUT at the same time, or else you'll have, imagine you're playing, let's see, what's a good example? Basically, your signals you might have multiple signals that all go into one decision forming thing, right? But if the decision line is staggered or offset by some time period, you're gonna have the wrong information with the wrong piece of information. Imagine you have like 5 different lines, 5 different people talking, and they're all supposed to be talking in like a conjoined way. But say this person says like the first piece of information, this person's supposed to say the first piece of information, this person's supposed to say the first piece. But it'd be a little bit weird if this person was actually already on their fourth piece of information, this person's on their fourth. You have one person that's on their second, and then maybe somebody's just now saying their first piece of information. It's going to make your device not work as intended. So whenever you have these high-speed signals, these fast-moving edges, you'll want to have these link tuning. Sometimes you'll have to have these link tuning just to make sure everything reaches there within some tolerance of each other. And that's done by making the lines themselves the same length. Within here, the tolerance is within within like 100 mil of each other. So here you'll see these ones are like red, but actually if you look at these blue lines, you can tell that there's bottom layer routing. So down here, you can see there's different layers. We have a top layer. Oh, we have a bottom layer here. We actually have some middle layers, but those are polygon pores, which are like ground planes, power planes. Don't think too hard about that right now, but they're hidden right now, actually. So one other thing I wanted to show you, on our last board, we only looked at the top. We didn't actually put anything on the bottom. But you can always put components on the bottom of your board. So if you look here, imagine we got a stencil for this board. We'd want to, you'd choose which side you want to use the stencil on, because you can't technically use the stencil on both sides. Because imagine you put the stencil down, you put your components on, you heat gun it or put it in the solder oven or something like that. And then you have your components set on your board, but then you go to the other side of the board and try to do the same thing. Then you put it back in the solder oven. That solder that you already put down is going to heat up again and reflow. And you could get things from like cold solder joints, but really what I would think of is just your components falling off the board, just falling down due to gravity. But yeah, so you'll usually want to choose which side you want to actually, which side you think is going to be more difficult, really, is the question to ask. If you are going to even use a stencil, because a lot of times we'll just solder both sides of the board by hand because we're not making like a huge number, or we won't put things too close together. But yeah, you can have components all around like this. Oops. I'll show you one more board and then we'll talk about layer stack ups. This one, no. Okay, and then so here, this is kind of like, we call this a universal board, a generic test board. And that's because you can put any arbitrary DIP 40 package into this DIP 40 socket here, socket it in, and then based on your pinouts on your particular circuit, you can connect different wires, different headers out here, and take the signals you need. You put in the signals you need, inject, take them out, put them into an oscilloscope, a source meter, use source meters to put them in, measure with a multimeter. Really, whatever testing you need to do for your specific board will be there. So next we'll go and look at some layer stack ups. So if you go to design, layer stack up, stack manager, it'll bring something up. I think you can actually also do this in KiCad. Set up. So yeah, if you go to KiCad, go to file, board setup, and then physical stack up, you'll see something that actually is really similar to what we have here in Altium. Oh, guess you gotta keep the whole thing open. Yeah, so you see here, it'll have the front silk screen, your front paste, your front solder mask. Your solder mask is the green part. And then here you'll see this one was called a 2-layer board because we have one copper layer, which is a signal layer. You'll have your dielectric there, which is FR4, but you can change it to something else if you do use a different one, like PTFE is, there's Teflon and PTFE, which are they're similar materials. We call PTFE Teflon. And that's kind of why their epsilon is the same. So then you'll have your bottom copper layer, your bottom solder mask, the thing that makes the bottom of the board green, solder paste, and your board paste, and then your silk screen. And then that kind of lines up with the board that we made earlier. So over here, you can also have different ones. I'll show you, this one's actually a 2-layer board as well. So you have your top overlay, your top solder, top layer dielectric, bottom layer. So this matches up with the copper. Altium actually makes it a little bit more visual because you see here copper's brown. So you'll see like this brown layer, you'll see your green layer up here, your top overlay, your solder mask and stuff. This will be your top solder paste or solder resist is what they'll call it. This is your solder mask, solder paste, signal layers, and then your dielectric in between. And then say, for example, this one here, this is a 4-layer board. So if you go to design, you go to your layer stack manager. You'll see here, you have the top overlay, the top solder, bottom overlay, bottom solder. Then you'll have a top signal layer, bottom signal layer, middle signal layer, and another middle signal layer. And then you'll see here, you'll have your pre-peg dielectric here in between. And pre-peg is generally just FR4. Then you'll have, I said that wrong. Pre-preg is not FR4, but then you'll have your core layer that is FR4. But these are all dielectrics. Okay. And then that should give you kind of like a general overview. What is layer stack up? What is a PCB? What does it do? How do you make one? So do you guys have any questions? Any questions? No? All right. That's about all I have for today. Hopefully that was entertaining, engaging, and helped you learn a little bit about PCB design. If you guys ever have any questions about that, you can feel free to drop in the Google Classroom or send me an email or things like that. Okay. Thank you guys. Thank you guys for coming and listening. It was fun. Give me one sec. I'm gonna stop the recording. Not know. Okay.